deep field. If you didn't get one, grab one on the way out. We have a picture of the ultra deep field on the front and a description on the back telling you about it. And our online audience can find it at the amazingspace.org website. It's lithograph number 36 among our resources there. So it's actually one of our earlier ones that we produced. Tonight we have an astrophysicist's guide to the film Deep Field, The Impossible Magnitude of Our Universe by Frank Summers from Space Telescope. So I am not just your host tonight, I'm also your speaker. You guys are an easy audience. April, we had a change of plans for April. I had two speakers who were available for the early April talk. Both of them had to cancel on me. But we have a symposium here on April 23rd, on the week of April 23rd, and they wanted to bring a special guest speaker from the symposium to do a public lecture. And so I said, great, I'll just move the April date until April 23rd, okay? So I think the normal date would be like April 2nd. Yeah, we're going to be 3 weeks late next month. I'm sorry. We're going to do April 23rd, a special date, but I promise you a special guest speaker. This speaker is so special that they haven't even told me who it is, okay? I've been in communication with them this month, and they said, oh yeah, we've got it. We're good, but we haven't confirmed, so we're not going to tell you yet. Okay. As soon as I know, you'll know. It'll be up on the website. In May, we have The Fiery Fate of Exoplanets. Sounds like planets that wander too close to their star by Jolene Karlberg. And in June, the question that everyone has been asking, can pulsar recycling produce a gamma ray excess? Yeah, I'll figure out what that means before next month, okay? This is a new astronomer in the Office of Public Outreach. He arrived about a year ago, Christopher Britt, and I finally have wrangled him into doing our talk. For the other talks upcoming, you can go find our website, go to your favorite search engine, type in Hubble Public Talks, and you should find this webpage with our upcoming lectures over here on the right. Links to our webcasting, both the live and the archives. Okay, we go back to 2014. I guess that's 5 years now. Wow. 5 years of Space Telescope webcast, of YouTube webcasting, and back to 2005. So that's, wow, that's enough 14 years of Space Telescope webcasting. If you'd like to get on our email list, you can also do there. Our email are basically just the announcements of the lectures, and when the webcasts are posted on YouTube, we let you know about it. If you don't like signing up on our website, you can write your email address down on a piece of paper, hand it to me after the lecture, and I'll make sure you get on there. If you have comments or questions, you can send them to our email, publiclecture@stsci.edu. And finally, if you are on social media, if you want to follow the Hubble Space Telescope, the Webb Space Telescope, or the Space Telescope Science Institute, we have Facebook, Twitter, YouTube, and Instagram for you to follow. I myself do a little bit of Facebook and Twitter if you're interested in my latest thoughts. Oftentimes after this, we have the observatory. Was it cloudy? Clouds are moving in. Okay, I did not receive a notification from the Maryland Space Grant folks, so I put a question mark here. I was assuming it probably was a no. All right. Anybody from Maryland Space Grant here? No. Okay. I'll ask. Remind me to ask again at the end, just in case, because not often we get a chance to go across. But you do get chances on Friday evenings when they're open houses. If you go to md.spacegrant.org, you can find this webpage over here. And on Fridays by 5 or 6 p.m., they will announce whether or not they're going to open the observatory Friday evenings for observing. Okay. All right. We are not going to have the news from the universe that I usually do. Since I am your speaker tonight, I didn't have time to prepare the news from the universe. So I will now introduce our speaker. Our speaker Our speaker is Frank Summers of the Office of Public Outreach here at Space Telescope Science Institute. He's been here since 2001, working on all aspects of Hubble Space Telescope public outreach, whether it's websites or educational materials or the news releases, or his specialty, which is scientific visualizations. And because he's an astronomer who makes movies, who does visualizations, he likes to call himself an astrophysicist. He also thinks it sounds kind of cool. It's just a play on astrophysicist who does visualizations. Let's see. I usually tell you something special about myself when I give the talks. I didn't prepare anything special. Before I was here at Space Telescope, I was at the American Museum of Natural History in New York, where Neil Tyson, Steve Soder, and I built the Rose Center for Earth and Space that opened in 2000. And before that, I did postdocs at Columbia and Princeton, and my PhD came from UCal Berkeley. So, ladies and gentlemen, while I switch my slides. Mr. Frank Summers. All right, can we get the lights down a little, in the audience down a little bit, please? All right, it is really fun to be here tonight, okay? Be able to show you this project that we worked on for about 18 months. Sometimes you get to work on really special projects, and this is one of them. It's going to give you my guide to Deep Field, The Impossible Magnitude of the Universe, this film that is based on a symphony called Deep Field by the composer Eric Whitacre. And the first question that people often have is, why would a Hubble image be deserving of a 24-minute symphony? Huh? What's going on here? So let's start with the Deep Field. And to explain the Deep Field, we're going to start here. This is the constellation of Ursa Major. Most of you know it as the Big Dipper, okay? We're going to zoom in, all right? So we're going to zoom into this region, go in a little closer, all right? And then we're going to zoom into this region and go a little closer. And then we're going to zoom into this region and go a little closer. And we'll go zoom yet further, get a little closer. And one more time, going in down to this field of view. Isn't that amazing? Yeah. We're talking about this rectangle right there. What can you guys see there? I can see like two fuzzy nothings there. In this ground-based survey, there's nothing there basically, right? Okay. So what would you say if prominent astronomers proposed to stare at this empty region and use 11 days of Hubble observing, a total of 140 hours of observing, looking at nothing? What would you say? It sounds like a crazy idea, okay? And you know what? A few astronomers at the time would have agreed with you, all right? So the idea behind this was to use the incredible resolution of Hubble and the fact that it's up above Earth's atmosphere and has this clear view to see as far out into the universe as we could see. All right? We want to see galaxies at their most distant. But the folks who said this was a crazy idea said, well, wait a minute. Galaxies, as they get further and further away, are going to get smaller and smaller and fainter, and eventually you won't be able to see them. And you could end up wasting a tremendous amount of Hubble time, and Hubble time is really valuable. You're going to spend 6 days of integration time on a blank field. But the director of the Space Telescope Science Institute at the time, Bob Williams, was convinced that if we saw something, it would be fantastic. And if we didn't see something, it would still be really good because it would show us the limitations of astronomy. So as the director, and using his director's discretionary time, he approved the original Hubble Deep Field project. The results were astounding. In this small, tiny field, they found over 3,000 galaxies stretching out to distances beyond where galaxies had ever been seen. This was the original Hubble Deep Field done in 1996, and it was so successful, it changed cosmology that we not only have this, but we had follow-on projects. On the right, you see the Hubble Ultra Deep Field that was taken in 2003 and released in 2004. It covered a slightly larger field with a new camera on Hubble, went even deeper than the original one, and found about 10,000 galaxies in a very tiny region of sky. How small? Well, I sort of did the zoom, but you sort of get lost on the scale of it. Let's compare the size of the Hubble Ultra Deep Field to the size of the full moon. Okay? It's really about the size of, one of these mare over here on the moon. Now, I know some of you probably think that the full moon is actually really, really large, and I have no idea where you could possibly have gotten such a silly idea. But if you take a real view of the full moon and you look at it, you can see that the full moon is only half a degree across on the sky. And the Hubble Ultra Deep Field being about, 1/3 or 1/10 the size of it, there are over 12 million patches on the entire night sky the size of the Hubble Ultra Deep Field. It is 1/12 millionth of the entire night sky. But in it, we see galaxies across the universe. And here are some details from the Hubble Ultra Deep Field. We can see big galaxies that are nearby, like here in the upper right. We can see medium-sized galaxies. We can see smaller and smaller galaxies. We can see flotsam and jetsam galaxies. And so this is a core sample through the universe, stretching out billions of light years through the universe, studying galaxies. And if you want to study galaxies in the universe, this is your Rosetta Stone. This is how we transformed our understanding of galaxies in the universe. So that's the story of why the Hubble Deep Field is so important. And it caught the attention of this man, composer and conductor Eric Whitacre. And he decided that he was going to write a symphony expressing some of this awe and immensity of the deep field. Now, I can't explain his reasoning as well as he can. I've heard him present this several times, but he gave me this slide here that is one of his drawings of how he sort of diagrams out his ideas for the Deep Field Symphony. And you can see that it has this opening up, starting small and rising up and making it big. And he talks about it being muddy and out of focus in the beginning, which is, to him, to sort of reflect the fact that the Hubble Space Telescope was, as you remember, out of focus to begin until after servicing Mission 1 when it was repaired and we brought it into focus. So one of his themes in his music is going to be take things that the music is going to be slightly out of focus and then come into focus. It's going to grow and progress forward and pull back, progress forward and pull back until it reaches this triumphant chord at the presentation of the Ultra Deep Field. And I'll explain some of the other things about it as I'm going through here, but he really has this full, complete idea of all these themes that he wants to do and certain notes and presentations and this golden brick idea of the repeating themes that he works through in order to try and express some of the majesty that you are presented with in this field. So he wrote this 24-minute symphony, and he conducted it. It had its world premiere in Minneapolis, Minnesota. And attending that performance was Bob Williams, the STSCI director, who had allowed the deep field to happen to begin with. And Bob, amongst others I'm going to understand, met Eric afterwards and said, you must combine this symphony with the Hubble visuals to make an incredible fusion of science and music together. So that's what Eric did. I actually think Eric probably wanted to do this already. He assembled a team, first starting with 59 Productions, a London-based production company that does unbelievable presentations. This is from their website where they put video onto the Sydney Opera House. The entire Sydney Opera House covered in video projections. All right, they put projections on castles and on 747 airplanes. They do amazing work in combining art and technology. And then, of course, he also came here to the Space Telescope Science Institute because we are the ones who have the Hubble images and we have the scientific visualizations of those Hubble images that bring things to life. So we just met with Eric, we showed him a variety of our work, and we started to talk through what we could do. Because, look, you can't show the ultra-deep field for 24 minutes, okay? This movie can't be just about one image, okay? What it really needs to be about is that journey to understand that image, that progression from what we see here on Earth out through the solar system and stars and nebulae and galaxies until you can get out to the furthest edge of the universe. And so we developed, in collaboration with 59 Productions and Music Productions Limited, this storyline of various ideas and everything. And it was all taking the music first and then trying to craft visuals that would do justice to this music. I will say here at the Space Telescope Science Institute, we contributed 11 sequences to this film, 7 of which we had already produced, and 4 of which were brand new. This is our team that worked on the 4 new ones, minus one person that you'll see in just a minute. This is myself, Joe, Danny, and Greg. We're down at NASA Kennedy Space Center last fall for the world premiere of this film. So we don't have a huge staff, okay? This is not like your latest Avengers blockbuster CGI fest where there's 500 people working on the computer graphics, okay? We got 5 here, guys, okay? But that's part of what made it such a special project for us because it was audacious and ambitious. So let me talk you through a variety of the sequences in the deep field. Matter of fact, I'm going to talk you through all of the astronomy sequences because when people sit down and watch it, I'm always getting people whispering in my ear, what am I looking at now? Oh, what's this? And I don't want you doing that during the film, okay? I want you to know what you're looking at. So I'm going to tell you all of the astronomy sequences that you're going to look at, all right? So the film begins with a view of the night sky. And actually, it starts out of focus and slowly, can you guys see this well? I'm not sure. This light is too bright. I need the light off the screen as much as possible. Nobody needs to see me, by the way, okay? They need to see the screen, though, so take some lights down. Yeah, astronomy has a major problem because we do a lot of black in our night skies. I think it's probably this one that's coming, the panel one that's shining on me. All right, well, I guess you can see it up on that screen. Okay, there we go. Thank you. Whatever that did, that worked. All right, and slowly it starts coming into focus until you can see the stars of the night sky. Now, that was what 59 Productions wanted to do to mirror the ideas in Eric's music of the music slowly coming into focus, Hubble, the flaw coming into focus, and the major transitions in the film include that change of defocus to focused. Right? And then this sequence leads on into showing you the Milky Way that goes across the night sky. And one of the other really great things that I love that they did was that as the music slowly built, it starts off with these hanging notes that are thin and just ring. And as this music builds and builds, they build the exposure, okay? So you start off seeing just the stars, but they increase the exposure so that you can see the full Milky Way as the music builds and it sort of just increases along with it. This sequence here was shot by our own very own astronomical image processor, Zolt LeVay. He has been our master image processor on Hubble images for many years and retired last fall just before this film was released. And not only dealing with astronomical images, he is an avid astrophotographer himself, such that he was given an artist in residence at Capitol Reef National Park last summer. And while he was there, he spent several nights getting these time-lapse imagery of the Milky Way. This is Zolt in his National Park official volunteer outfit. They told him he got to keep the shirt but not the hat, or vice versa. I can't remember which. All right. Also, this shot over here on the right is from Capitol Reef, and it shows a very important thing, that right there. Now, many of you might look at that and go, oh, that's a meteor trail. No, it's not. It's an airplane, okay? Capitol Reef National Park is out in the middle of nowhere, but it's not so far out in the middle of nowhere that airplanes don't fly through. So in Zolt's time lapse, over 70 airplanes flew through his time lapse. There was an intern at 59 Productions who spent his entire work on the project removing those airplanes from the Milky Way thing. So the fact that there are no airplanes in the Milky Way sequence, you can thank that intern at 59 Productions. The other cool thing about the Milky Way shot is the defocus at the end of it. And they defocus out. You can start to see there's this funky little pattern here that they use for the defocus. It's not just a circular blur. This is, in fact, the point spread function of Hubble before the flaw was fixed. So this is actual a scientific image that Hubble would take of a point in 1990 before the flaw was fixed after the servicing mission one. So that's just a cute little thing that they threw in one of the defocusing things to throw in the point spread function from Hubble. All right. The next set of sequences is the solar system. We here at Space Telescope did not work on them because these are all NASA missions that go through it. Begins with the moon from Lunar Reconnaissance Orbiter. These are wonderful, wonderful pans. And I will say that while I was at AMNH, people would come to me and say, wait a minute, we went to the moon and all we took were black and white cameras? And then, of course, you show them, all right, well, yeah, we went to the moon, but these are color photographs of a black and white world. All right, so yes, the moon is just black and white, but that's the way the moon really is, not because we're not colorizing these things. If you want color, you get it in the next sequence from Mars, a whole sequence of images from Viking and from Mars Global Surveyor. Incredible details of the surface of Mars. The Jupiter sequence comes from the mission Juno. And Juno, I don't know if you know, is a mission that's designed to study the magnetosphere and the atmosphere and the interior of Jupiter. It really isn't a imager. It doesn't take pictures. None of the science data from the Juno mission are pictures. What we see from Juno is actually an instrument called JunoCam, which is essentially a webcam added to the scientific mission. They recognize that we're going to get this incredible data about the magnetosphere of Jupiter, but the public loves their images. So they put a space-hardened webcam type apparatus on it. And when Juno makes these gorgeous these flybys, they get these gorgeous images of the cloud tops of Jupiter, and really has been produced much more amazing images than I ever thought would be possible with the level of camera that they put on it. And you'll see tonight that they're just amazing. Finally, the last planet visited is Saturn, and you might look at this and say, well, why did they put in a still shot of Saturn? It's not a still shot. You must watch for these objects right there. Those are the moons of Saturn, and you will see them move through it. Saturn itself doesn't change much in the shot in the film, but there are 5 moons, 4 here. There's a 5th one that enters at the top of the screen. That will be part of it, okay? And that's the movement that covers the planets. The next movement in the film covers the stars and nebulae. So the symphony changes a bit and brings in our nearest star, which is, of course, our sun. This is the sun in ultraviolet light from the Solar Dynamics Observatory. And when you see that and hear the chord that comes with it, you will start to hear the presaging of the magnificent chord that will happen with the deep field. And this one comes in, and it's slightly out of focus. Right? When I first heard it, I was like, what's he doing here? I was like, oh, is this out of key or what? It's intentionally slightly out of focus so that the music clarifies over the course of its development. All right, and so this is a really nice way of presaging what he's going to come up with. We pull out of the sun, and then we start to fly through a star field with the Milky Way in the background. So escape out of our solar system, starts flying through a star field. And this shot here was based on a shot that I did for a documentary filmmaker flying towards the Orion constellation. And I just want to mention one thing about it because it's going to come up in different pattern later, that the Milky Way is so big that when you're flying through the local stars, the Milky Way doesn't change that much. So we use a standard technique where we have a star field. And the star field is rendered in 3D, and we fly through it, and the stars are all flying past you. But the background is just a Milky Way that's a static 2D image, okay? So we have this foreground background thing to make our computation easier, because trying to build out a full Milky Way, that could be a difficult project, right? Yeah, you'll see in just a minute. So this foreground background, I just want you to keep that in mind for later. We fly through the stars and we come up upon the star-forming region Sharpless 2-106, which we just call S106. And this is the beginning of a sequence of 4 massive star sequences, all right? In the center of this is a star-forming region. We've just formed a very massive star at the core of this nebula. And the winds from this star and the ultraviolet radiation from this star have carved this nebula. There's probably a disk of material around this star here in the center, which constrains things in that direction and allows the winds to blow out in opposite directions, creating this hourglass shape to it. And we knew enough about the 3D structure of this that we could build the model, and we actually fly down onto it. 59 production then takes us flying through it, transfers over to the next nebula, which is the Bubble Nebula, a visualization we did in 2016, another massive star in the core of it, and it has had ejection of a wind, all right? And that wind has got this bubble that is being blown in the center of this nebula. Now you may look at this bubble and say, hey, wait a minute, how come the star is off-center? That is actually correct, that it is off-center, because the nebula is on the left, and the nebula has a pressure from it that resists the flow of the bubble, the wind that's making this bubble. On the right, the nebula is not there, and it is able to expand more freely and expand so that this star actually is off-center within this gorgeous glowing bubble of the nebula. The next nebula is the Lagoon Nebula. This was a visualization we did in 2018. And again, you see a massive star here. This one is actually hidden behind a lot of dark gas, but its radiation is causing the cool colors within the nebula. This visualization also then rises up through the rest of the Lagoon Nebula and shows you some gorgeous ionization fronts. They're red ridges along the edge of the dark gas where the ionizing radiation hits the gas and causes the gas to ionize. Gorgeous little ionization fronts. Look for them in that sequence. And the last of our massive star sequences is a massive star cluster, a cluster of massive stars called Westerlund 2. And Westerlund 2 has one of the largest collections of massive stars in a cluster within a nebula that's called GUM-29. And I'm going to tell you a bit about this one so you can get an understanding of how we visualize sequences like this. All of these sequences are visualized using a similar technique. So here is the Westerlund 2 image that we used for the visualization. The center region is the Hubble image, and the outer regions come from a European Southern Observatory larger image of GUM 29. And the first thing we're going to do to visualize this is we're going to get rid of all those stars. I love being able to do that with one click. That, as you might guess, is a tremendous amount of work by our image processors. They do some fantastic work. But we got to get those stars back, okay? And we're not going to go in and cut out images of every single one of those stars and paste them back into our 3D model. Instead, we're going to use something that I like to call PSF stars, or synthetic stars, all right? So we can go through with our astronomical software and identify all the stars in the images. And we've got them in several different filters, okay? The 555 is in the middle of the visible, this is in the red, and this is in the infrared, okay? And so here's an image of all the stars in the Hubble image that are there, and their colors. So we can measure the brightnesses and colors of every star in the image and put them into a catalog, okay? We also know a lot about the point spread function of a star. We know how it goes from a very small dot to a larger and larger and larger, and how the light spreads out across the Hubble detector. So if we know the brightness of the star, we can predict accurately what it will look like on the Hubble image. All right, so using this catalog together, we can create the colors of the stars, and we can create the look of those stars synthetically without having to go back through and Photoshop and cut things out. We can do it scientifically. All right. The other thing we need to do is actually separate out which stars are in the foreground and which stars are in the cluster. And we do this with a scientific measurement, which we call the color magnitude diagram, a CMD. And it's basically a color diagram. And you can see the ones highlighted in red here are the ones that the scientists we were working with identified as these are the ones that are in the cluster. And this big, long, white swath of ones, these are the ones in the foreground. And so we're able to map out, and we subtract out the cluster stars. You can see there's a little residual, but overall pretty good. And that takes care of the Hubble stars. The other thing we can do is we can go to the 2-mass catalog and pull in the stars in the rest of the field, all of these white stars here, use the 2-mass catalog, match them to the Hubble band passes, and reproduce stars in the external part of the field. So we can recreate all the stars and statistically distribute them around the nebula for the thing. So now we've got to get back to the nebula itself. And this nebula is done with a process that we call sculpted decoupage, all right? To illustrate that, I'm going to take this image, the Great Wave of Kanagawa, and if you cut it up, we make multiple versions of it, and you cut it up into its various pieces, and you put little spacers between them, you create what is called a decoupage box. And it gives you a 3D look and feel by having multiple flat layers. So we do this same sort of thing, but we do it digitally in a 3D modeling program. And we also, instead of using flat layers, we sculpt the various layers to give them texture and feel. So in our digital program, we have this type of configuration, all right? So the camera is up here, looking down at the nebula here. And what's highlighted in white here these are the background layers of the nebula. Then we have the pieces that are inside the nebula, the pillars and all of the structures inside the nebula. Then we have the layers that are at the front side of the nebula, the dark gas and such, and the gas that's being irradiated by the stars, as well as there is this small little fluffy stuff in front of it, which we call the veil of the nebula. It's sort of gas that's been blown out of the nebula in the direction toward where we are looking. Plus, we've got in this model the cluster stars down here, the Hubble stars here, statistically distributed in front of the nebula, and then the 2-mass stars, the ESO stars, statistically distributed around those. All right? And this is how we create, well, I guess I call this the Christmas tree of our model, we've got about 25 layers of the nebula and about 25,000 individual stars floating in 3D that we're going to pass the camera through. Put that visually, this is the build sequence starting from the back to the front. So the background behind the nebula, pulling in the cluster stars, all the pieces that are inside the nebula, many of these, the pillars that are pointing toward the cluster at the center. So we get to the front part of the nebula and then the veil. We bring in the Hubble stars and the stars. This is the full 3D model as you watch it that we then fly through to build for it. So this same sort of sequence of sculpted decoupage procedure is what we use for all of these nebula sequences, and we'll actually also use it for one of the galaxy sequences I'll show you in just a minute. All right, back to the film. The nebula movement ends, and we go into the galaxy movement. And the galaxy movement begins with probably the toughest shot in the entire film. This was the galaxy traverse sequence in which we had to fly through a Milky Way galaxy. We flew out of our solar system and through the stars of the galaxy. Now we want to escape the galaxy and go out and explore other galaxies. And I got to say, I probably spent 4 to 6 weeks working on this sequence. So I'm going to tell you about it because it was quite a lot of work. It began at the Astroviz conference that was held in Pasadena last summer, where the astronomy visualization experts got together and chatted about things. And somebody showed this image. This is gas and dust in a spiral galaxy, but it's not an observation. This is a computer simulation that looks so realistic. Okay, this is the fire simulations, the feedback and realistic environment by Hummels, Hopkins, and Wetzel, and Cameron Hummels, who presented it. I said, oh, I got to get this data. This is so cool. I can use the visualizations of this could be fantastic. So they had, this one is a Milky Way analog with 150 million points and all the details of the star formation going on there. I said, great, let's take a look at this. And I played with it and I got to visualizing it. And I said, fantastic, look at this. This just feels like a galaxy. Look at all the dust and all the stuff. It's just, oh, wow. All I got to do, all I got to do is just fly through this. And I said to myself, hey, it's Sunset Boulevard. We're ready for our close-up, okay? I was thinking this was going to be the simplest sequence of all. And then I tried it. And it looks okay here, and as you get closer, it starts to break down, and as you get inside it, it's blah. It looked, and I could adjust the parameters and play with it, and I could get, okay, I can get the foreground star stuff here, but look at that background stuff. It's just all muddy and disgusting, and I was going back and forth because I wasn't getting what I needed, which is this. This is an image of our Milky Way, okay? And you can see this beautiful structure of the dark gas and all the light, the brightness of the halo in behind it and stuff. It's like I couldn't get it until I smacked myself in the head and going, dude, you can't see that dark stuff unless you got backlight, right? You really need to make sure you get the full backlight in behind your dark gas. Otherwise, the dark gas is just, it doesn't add to your picture. So remember that foreground background stuff? I had to go back to that foreground background and reinterpret it in 2 new ways. So my multi-layered star viz had to have the foreground, okay, which was the same as I did for the star thing. This is the Hipparcos catalog of the foreground stars. These are the bright stars that are in the near ground. And for that, I only generated those stars along the camera path, because there's like 100 billion stars in the Milky Way. I'm not going to generate 100 billion stars. I only generate the ones that I need that are along the camera path, so I get, tens of millions instead. Then I created the midground, which was that standard point cloud viz that I just showed you, and that all worked. But I recognized that when doing the midground, there's a lot of stars that were too faint and too small that you just ignored because they weren't bright enough to be seen. But that light was getting lost in the procedure. And so I collected all that light that was individually too faint to see, but adding it together provided this 3D background. So instead of having a 2D background for my galaxy, I added in a full 3-dimensional background that could then illuminate those dark dust clouds, all right? And then I was able to produce a test image like this, and I said, yes, I'm starting to get some dark dust clouds. I can deal with this. This is great. And then we worked for couple more weeks and got to here. The procedure for this is a shot from the film. And one of the cool things about it was that in the simulations, they had all the information on the star formation. So these red clouds here and these blue clouds here, these are emission and reflection nebulae that are tied to where stars have recently formed in the simulation. Because I got the information about when stars have formed in the simulation, and the gas around the newly forming stars will be it will be heated up and will glow red, or will, if it's a little older, will actually reflect the light of the newborn stars and glow blue. And I know that no one will ever notice that these are actually the correct star-forming places in the galaxy, but I know, and it's really geeky cool to be able to say that, yes, these are the right places for those H2 regions and H1 regions in the galaxy. All right, so we fly out of our galaxy in this sequence, and we come upon one of Hubble's most famous galaxy observations, the Whirlpool Galaxy, okay? And this is the Hubble visualization of it, and I'll go through this just relatively quickly because this was another major project here. So this is Hubble's observation of the Whirlpool, and we didn't want to deal with the satellite galaxy, so goodbye. We erased it for this. And then we had to separate this into its various components. And you can see you've got these old stars here that are sort of yellowish, the young stars here, which are sort of bluish and greenish, and then you've got these red star forming regions here. And we first tried doing the standard RGB separation, red, green, blue separation, and it really didn't work. And then I hit my head, oh, we've got sort of cyan and sort of magenta and yellow. We're going to do the CMYK separation, color separation. If you've never heard of it, don't worry about it. It's a standard color separation using cyan, magenta, and yellow and black. And these were the three, the cyan, magenta, and yellow separations of the image, which we could then transform into the young stars from the blue, from the cyan, the emission nebula from the magenta, and these are pink, and the old stars that are yellowish and whitish. And so now we have two-dimensional images that sort of separate out the various components of that galaxy. We also could use the black to do the dust lanes in the galaxy, and Hubble's dust lanes are fine. But really, if you want to look at dust, you want to go really into the infrared. So we also use the Spitzer image here to get the dust lanes for the Whirlpool Galaxy. All right, combining these, we had to use what we call point cloud visualizations, taking those images and creating point clouds above and below those images. So these are two-dimensional images. So you make them 3D and you give them the right density structure and the presentation and everything. And we ended up creating about 100 million point clouds. And we have custom software called Pointillism to handle it. And the sequences were a little heavy. They hit my maximum, which is about 3 CPU hours per frame. That's not frames per second, it's hours per frame. 3 hours to render one frame of this sequence at 4K. That's usually my maximum. I don't like to go beyond that. Fortunately, 100 million point clouds was doable in that for this project. Okay, we rendered all of them separately. So we have the old stars here, we have the young stars here, we have the emission nebulae here, along with the cluster stars inside those things, and boom, together they form the Whirlpool Galaxy. Now I'm going to digress for one little second here, okay? Because we went further than this with the Universe of Learning. We have our educational project here called the Universe of Learning, and Hubble isn't the only one that has observed the Whirlpool Galaxy. As I've already used the Spitzer image, and the Chandra X-ray Observatory observed it as well. So we went further, and we took the Spitzer data and the Chandra data, and we made 3D models for them as well. So we've got the 2 wavelengths of infrared and 2 energies for the X-ray. Combining them, we can cross-compare between infrared visible, and X-ray in a short little film that we called Shedding New Light on the Whirlpool Galaxy, giving you a visual representation of the value of all these NASA observatories and the strength of doing multi-wavelength astronomy. This is an example of one of the sort of educational, the learning projects that we can do with NASA's Universe of Learning based on some of these visualization projects. All right, back to the film, all right? The galaxy sequence continues with a new visualization we did of Stephan's quintet of galaxies. And this over here on the right-hand side, those 5 galaxies are what's usually called the quintet, although they are actually just a quartet because this blue galaxy here is a foreground galaxy that happens to be projected along the line of sight. But while working on this project, I also learned that this galaxy over here is on the left is at the same distance as the main grouping. So this quintet that's actually a quartet is really a sextet that's really is a quintet. All right. So the point of all this is that galaxies can be found in these groups together. We fly through the quintet of galaxies in the movie and take us into the Candles Galaxy Survey. One of the largest visualizations we've ever done, 35,000 galaxies stretched out across space. We did this in 2017, and we fly through this as a preparation for seeing the Hubble Ultra Deep Field, and we hit the climax of the film, and you get that resplendent chord that Eric has been building up to. And when you're flying through the Hubble Ultra Deep Field, we want to tell you a story, and it's a story I think you all are familiar with. The story is a long time ago in a galaxy far, far away. Now, this is one of the things that George Lucas accidentally got right in Star Wars, because galaxies that are far, far away are galaxies that are seen a long time ago. The light from a galaxy can take billions of years to cross the intervening space before we see it. So if the light from the galaxy left it 5 billion years ago, we're seeing that galaxy as it was 5 billion years ago. All right? A galaxy that's 10 billion light years away, we're seeing as it was 10 billion years ago. If we look at galaxies nearby and further away, their morphology changes because galaxies develop over these billion-year timescales. We can see the development of galaxies. We look out into space, we look back into time, and we can see how galaxies have developed over the history of the universe. And that's one of the most powerful things that we find in this Hubble Ultra Deep Field. So to do this, we actually have to have the individual galaxies. So we take this Hubble Ultra Deep Field, and effectively we just cut little postage stamps around every single one of these galaxies. Now, we're not going to do this by hand, okay? Somebody would go crazy. We actually have scientific software that does all this, and we pull out those little postage stamps and we bring it into our 3D software. Now, this dense region in here, that's the Hubble Ultra Deep Field within the much larger Great Observatories Origins Deep Survey, or the GOODS field in our 3D. And these are just the rectangles representing the galaxy images. And if we look at it from the side, the camera's over here, we're looking down through it, and you can see this big, long pyramid of galaxies stretching out across the universe. And I wanted to show you this because I wanted to admit to you that we cheated here, okay? I like to tell you when we cheat. This pyramid should be about 500 times longer than it is, okay? The universe is a really, really, really big place. This is a very long and thin pyramid. But if I did it scientifically correctly, instead of flying through it in a minute, it would take about 8 hours to fly through it. And I don't think you guys would want to sit around and wait 8 hours to fly through the Ultra Deep Field. So we scrunched it up so that we could fly through it in a reasonable amount of time. Plus, there's one other cheat that we did, but it has a really good reason for it. Because when you look at the most distant objects in the deep field, they are the galaxies that are the furthest away, seen at the earliest times of the universe and the earliest development. And they are these red dots, okay? They are the galaxies who are redshifted the most, so their light is all the way into the infrared, and they're just beginning to develop. They could be even called proto-galaxies, so they're just blobs, all right? These are the most important galaxies that we find in the ultra-deep field because they show us the earliest stages that we can find in the Hubble ultra-deep field of galaxies. And I wanted a red dot galaxy to be the last thing that you see. So in this shot, as we exit the deep field, this galaxy right here doesn't belong there. It's actually in the ultra deep field, okay? But I had the guys at 59 Productions take it from where it was and push it into our field so that we could fly past, and this would be the last galaxy you see, okay? So I cheated, but there's a scientific reason behind that cheat so that a red dot galaxy would be the last thing you see. All right, so we've taken you through the whole universe, right? And we're sitting out the edge of the universe, and we're just going to leave you there. No. Now we bring in Eric's pet project, the virtual choir. All right. And so after we get through the whole universe, and suddenly these swirls start appearing, and they're really cool. This is a cool graphic effect. I honestly, when I first saw these, they reminded me of the trails left in old particle physics experiments, but they're not. They are actually Eric Whitacre conducting the universe. When he conducted the orchestra to record this symphony a second time, they put Eric in a motion capture suit. They recorded his motions, and Eric is a performer, okay? He is a performer, okay? And I think you can sort of see, can you imagine his baton here and his arms swaying and swishing? These were generated from the motion capture of Eric conducting the symphony. So that's a kind of cool thing that you'd never know unless you came to this talk, okay? And then this segues into the virtual choir, okay? And all of these singers floating through space. Now, Eric started the virtual choir after this woman named Britlin posted a video on YouTube of her singing one of Eric's songs as a dedication to him. And of course, he was flattered and everything, but he said, wait a minute. If I got a bunch of people to record themselves singing, I could sort of put them together into this virtual choir of people who never met each other, but were all singing in unison. So he uploaded a video of him conducting one of his pieces, Luxorumque, and the singers sat in their living rooms or dining rooms or bedrooms or whatever and recorded themselves singing to his conduction, and then submitted his videos, and his team put it together for his virtual choir. Here's Eric doing the conducting, and here are all the people singing their various parts from totally distant places. All right? He such a success. The choral people absolutely loved it. He did it again with a whole bunch more people, separated across all various countries, and did it again with thousands of people, and then upped it so that we had a 3D. They had a 3D Eric conducting all these people. Okay, so Deep Field was to be the fifth incarnation of his virtual choir, and he got more than 8,000 singers from around the globe to submit. So you will see 8,000 singers in this film. And this is the reason why the credits take 6 minutes. Every single one of these virtual choir singers is in the credits, okay? But because they were working with us, and I gotta give Music Productions a huge hand, they wanted to include science and technology in it. So not only did you upload your video, you also had a chance to earn these badges on their website. There were 18 badges. Anybody recognize this pattern? Yeah, the James Webb Space Telescope pattern of hexagons. Each one of these is a separate badge involving science, technology, engineering, art and design, and math, so-called STEAM education. For example, one of them was the Hubble Ultra Deep Field Sonified, where if you ran your cursor over these things, the redshift of the galaxy gave you a note that was really low if it was far away, or very high if it was nearby. And you had a sonification, all sorts of amazing things. And I just was like, these these are partners you want to work with, okay? These are the kind of people you really want to work with because they don't just do it halfway. They really go all the way to combining science and art together. All right? So now we begin the return home, the final sequence of the film. All right? And they came out through the Hubble Space Telescope sitting over Earth. And I got to be honest with you, Greg Bacon and I, when we saw this sequence, said, this is kind of trite. So many documentaries have the camera moving through the Hubble mirror to see things. And it's like, all right, okay, I guess. But we changed our minds because by coming out with Hubble here, by bringing the camera out, returning home with Hubble, it puts you in that low Earth orbit from which you can then go into a sequence of space shuttle shots of the Earth. And so the next sequences are these gorgeous space shuttle shots. Here's one. It took me a while to figure out these things. This is Baja Peninsula here and the Gulf of California. California's over here. Arizona's here. All right. You get the shot of Switzerland down bottom, the Alps running across the center, and Italy up here. And then the amazing shot of the Nile River Delta. All right, these wonderful shots from space bring you back home, show you the beauty of our planet, and then they bring back the virtual choir. And they fill the screen. They cover the Earth with this virtual choir. This is a global choir. They're getting that point across to you that this is a truly global choir, and you saw from the map that it really is. And finally, the last sequence, simply our Earth, hanging there in space. And Eric says that he really wanted to bring across that Carl Sagan point of view, the idea that looking at our planet from outside, seeing it there hanging in space, changes your perspective. And through this, you really can, with this film, you truly can connect those dots from that tiny red dot galaxy out at the edge of our observable universe, across 13 billion light years of space, to our pale blue dot that we call home. That expanse, that expression, that truly is the impossible magnitude of our universe. Thank you for your attention. Okay, we are going to end the webcast now. So for the folks who are online, you can watch the film. It is already available at deepfieldfilm.com. All right, and please, for the best experience, watch it on a big screen in a dark room with really good sound. I suppose you could probably watch it on your phone. I mean, I'll shed a tear, but it's better than not watching it at all, okay? So please, if you can, watch it nice and big, all right? Thank you all for joining us online. I hope you've enjoyed this expression of this film as much as we here at Space Telescope, and in collaboration with 59 Productions and with Music Productions. We had a great time presenting it, and we really hope you enjoy it. Good night. Okay.